canonical extensions of Quantale enriched categories. This sounds like extremely technical, but I think there's a kind of a big idea that a lot of people pursue who are working in, say, the intersection of logic and theoretical computer science, and that is the idea of kind of generalizing techniques that were established for two-valued logics to many-valued logics. So we want to use this in software engineering for quantitative specifications and verifications of software. So instead of having true and false, we also want to have kind of how similar something is, like metrics, for example. So metric spaces, that's a topic here. So Quantale enriched categories, they include metric spaces as special cases. Yeah, but the slides itself are fairly technical. So I want to say that right at the beginning, what really interests me is here using these techniques, applying these techniques, right? And so I think that is a topic that is interesting also for our guests here and could be something to explore between Topos and Chapman in the future. So for example, yesterday we talked about relations, but then there are also many valued relations, right? So that will play a big role in the following. And the emphasis of this presentation is really to set up things in such a way that the generalization from the two-valued to the many-valued setting is as smooth as possible. So I want to write exactly the same formulas, and they should kind of look similar enough to what we do when we do lattice theory or order theory, but also they should work well if I think of them as instances of category theoretic notions, not order theoretic notions. So that's kind of the aim of this presentation. Okay, so I start here with ordered structures, which would, and of particular importance are complete lattices here. And so what this slide shows is a way of building complete lattices. So this goes back to Dedekind cuts. There has been work by McNeil. I found Birkhoff's early book on lattice theory from 1948 has all of that and more already. So how do we build a complete lattice? So there are these two sets here, X and A. And this notation comes from database theory. So X is kind of the objects, the set of objects we want to talk about. And A is the set of attributes we want to use to talk about the objects. And then they like to use the letter I for incidence relation. So we should read this as object X has property A. That's the idea. And so then the two important operations are like given an object, what are all the attributes that it satisfies? And then vice versa, given an attribute, what is the extension of that attribute? What is the set of objects that satisfies this attribute or property? So these are these up arrow, down arrow things here. And then also we want to kind of generalize this thinking of Dedekind cuts, right? So everything above and everything below, but if you use Dedekind cuts to build the real numbers, you take everything above of a set, right? Not just a single element. And vice versa, you take everything below a set. And so if you picture kind of the line with the Dedekind cuts, right? So then a cut consists of a down set and an up set, right? The same is going to happen here in general. So this is why the two operations, the up arrow and the down arrow notation, are going from down sets of X to up sets of A. So this is the notation dx and ua, and vice versa from ua to dx. This also has a logical interpretation, right? So you see that there's you look at the slide, the up arrow and the down arrow notation correspond to universal quantification. And so if you look at the formula with the universal quantification in there, then you can see that I rewrite this in a different way using a conjunction and an implication. So this is the notation which will generalize to the many-valued setting. So it's not the first order notation that smoothly generalizes, but it is the kind of propositional logic notation with the conjunction and the implication. You can, another thing I want to point out here is that you can see that I write the implications in two different directions, right? So in two-valued logic, these two implications are the same implication. We never write it from right to left using a different symbol. So I didn't say what a quantile is yet, but one thing a quantile is, one thing a quantile does, it replaces the conjunction, the binary conjunction, by a binary operation, fusion, multiplication, comes under different names, but it doesn't need to be commutative, right? And if we have non-commutative multiplication, then we get two implications. So when I started working on this, I really wanted to cover the non-commutative case, because Peter is always saying everything works in the non-commutative case. From a category theoretic point of view, it's slightly inconvenient, because when it comes to the commutative case, we can just take Tallis' book on enriched category theory, and it's a wonderful book. Everything is there, but everything in there almost from, I think, page 5 onwards assumes commutativity, or rather symmetric monoidal categories. So I was really forced to think about what notation should I use in for this work. And it is the case that there's a lot of work out there in category theory on the non-symmetric case, but everybody is kind of inventing their own notation. And so I felt free, like, also inventing new notation here. But as I said, this notation is not arbitrary. So my co-author, Apostolos Gimoulis from Amsterdam, who will actually come today, he will be here in the evening. He's really working more in algebraic logic and order theory and lattice theory. So we developed this notation in collaboration to find a good compromise. And this compromise is this black triangle notation. So this will play kind of a role in this talk, and sometimes I just call it the black triangle calculus. So it turns out that these symbols have satisfy its own algebraic laws, and we can use them to just do algebra. But also the laws that these black triangles satisfy it really comes from the quantile, right? So there's a lower level and a higher level, and this level is connected, and I try to find notation where you can kind of see that the lower level notation corresponds to which higher level notation. We'll see this in detail later. Then maybe another thing I want to point out here is that actually once you start working with this and you give up commutativity, the notation becomes actually better. Like if you look at these two lines at the bottom, I don't know whether you agree with me, but writing the implication from right to left in the second case actually makes these formulas easier to remember and understand, right? Because one formula is about upsets and the other is about downsets, right? So it makes sense to write the implication in one direction for upsets and in the other direction for downsets. Moreover, if you agree that downsets are on the left and upsets are on the right, kind of the notation becomes very intuitive. Okay, so to summarize, okay, I'm not allowed to move. Let me see whether I can highlight that. Yeah, I cannot really highlight that here. So this equation, the first one, with a black triangle to the right, so phi black triangle right I, that takes a downset and maps it to an upset. Right, so we think of moving the phi from left to right. So that's how I read this triangle. And then the other one takes an upset psi from the right to the left, as the arrow indicates. So it takes an upset into a downset. That is kind of the idea how that is supposed to work. Okay, so I have an example here, which I was hoping there's maybe a whiteboard or a flip chart. Obviously, we should draw this incidence relation as a picture, where the x's are at the bottom and the a's are at the top, and then we draw a line. And we can compute the up arrow operation and the down arrow operation. And then we can say, okay, so really what we're interested in here are the fixed points. So I take an arbitrary subset of x's, I map it to the right, I get an upset. I map it to the left, I get a downset, and that's a fixed point. If I keep going around, I stay, I don't get kind of new subsets anymore. And vice versa on the other side. So that's the so-called Magnier completion, right? So if you think of Dedekind cuts, that's exactly kind of like you take all upsets, you take all upper bounds, then you take all lower bounds. Even if you don't start with a downset, that gives you a closure operator on downsets. And similarly, you get a closure operator on upsets. And then these closed elements, or the fixed points, they are what constitutes the Magnier completion, or the Dedekind Magnier completion. So that's a way of getting real numbers, for example, from rational numbers. And so what we will be looking at is this Magnier completion. And so you could only work on downsets, or you could only work on upsets, but the notation becomes better in my view if we keep a pair. So it's really a cut. It's a downset and an upset together. And then the condition is that the upset is the upper bounds of the downset, and the downset is the lower bounds of the upset. So each side determines each other, and we can use this to work on whatever side is convenient for what we want to calculate at the moment. Okay, so this is all the classical Magnier completion. And as I said, I found this, the earliest reference, which is kind of doing it exactly that way, I found is in Böcker's book. Okay, so now we want to move from two-valued logic to many-valued logic. We want to move from ordered structures to metric spaces, right? So that's the idea here. Keeping the math working in exactly the same way. So, so what is a quantile? It's a monoid in the category of soup lattices, so complete joint semi-lattices. And what this means is that we have an order relation, we have arbitrary joints, and then obviously we have a neutral element and a multiplication. And the multiplication needs to be an arrow, a bilinear map in the category of soup lattices, so it preserves the joints. And that it preserves the joints means that it has residuals, a right residual and a left residual. So here you see now the white triangle version of the black triangles, right? And the laws that the black triangle satisfy come directly from the laws that the white triangle satisfy. But there's a different level, right? So the white triangles are operations in the quantile. They're kind of the meta logic, right? So we were moving here from Boolean logic to a meta logic, which is the logic of the quantile. So we have conjunction and disjunction. And then we also have this multiplication together with its two implications. So the most interesting commutative example, so where the multiplication is commutative and the two implications coincide, is the so-called Laurier quantile. So this quantile has the real numbers from 0 to infinity as the elements of the quantile. And then the order goes the other way around as the natural order. So 0 is the top element and infinity is the bottom element, which kind of, if you think of truth values, that's what you want, right? If 2 points have no distance of each other, then they are equal. So it's true that they are equal. So 0 should be top. And then if they're not equal, then you can measure the distance. How much are they not equal? So that's the intuition. I didn't talk about categories yet, or categories enriched or anything. But let me say at this point that categories enriched over the two chain with conjunction and ordinary implication, that's a quantile, right? And the categories enriched over this are just the orders. So that's kind of the connection now. The categories enriched over the Laurier quantile are metric spaces. Actually, they have a little bit more properties, so you have more freedom. For example, the metric doesn't need to be symmetric. So you can have distance 0 in one direction between x and y, but then y doesn't have to be, but y doesn't have to be smaller or equal to x. There can be a proper distance from y to x, even so the distance from x to y is 0. This is also an interesting remark here, is that these categories enriched over the Laurier quantile, they unify both orders and metrics, right? So if the distance from x to y is 0, then you read this as x is smaller or equal to 0. So the same structure can be an ordered structure and a metric structure. Typical situation, x is smaller or equal to y, that's order structure. Y is not smaller or equal to x, but now you have a distance. How badly fails y to be smaller or equal to x, right? So you have order structure and metric structure. This is an idea that had been very influential in theoretical computer science, that has been used to unify models of programming languages. So we have to model recursion maybe, as you know. So how do we model recursion? We use either ordered structure or metric structures. And like in the 70s, 80s, there have been kind of two competing ways of doing domain theory. So one is the ordered way of doing it, and the other is the metric way of doing it. Then motivated by this discovery of Laurier, people started to work out kind of a unified domain theory where the domains are these Laurier metric spaces. And then you can prove fixed point theorems, which give you the denotational semantics of recursive functions that equally, so that they have an ordered interpretation and a metric interpretation, because they have fixed point theorems for these that work with these Laurier metric spaces. And then the other examples are interesting to me here because they are non-commutative. So the quantile of all languages. So what would be then a category enriched over this quantile? You can think of this as automata, right? So what that means is you have a state. So these are the elements of the category, the objects of the category. And then, so usually when we draw an automaton, right, so we have these states and we label the edges with letters from an alphabet, right? So, but then you can think of, oh, I can also compose two of these actions, and then I should label the composition, say, I have label A, label B, right? So then the composition should be labeled AB. So now we don't label with letters anymore. We label with words. And then if you push this just a little bit further, you can have different paths from one state to another state. So if you want to account for that, then you need to label with sets of words, right? So that's extremely intuitive, right? So the label is the language that leads you from the first state to the target state. So categories enriched over the Quantale of all languages are just kind of a generalized version of non-deterministic automata. And then it's actually quite fun to think about, oh, what is the meaning of these residuals? And later maybe we'll talk a little bit about weighted limits and co-limits. So what do they mean in this setting? So one can reconstruct classical notions from automata theory, like the Borzowski derivative, using this idea of weighted limits and co-limits, for example. Okay, so just for the language, I call categories enriched over a quantile omega and omega space. And really, these categories, they look more like metric spaces than like what we usually think of when we think of a category. So I think the terminology of a space or an omega space is makes sense in this setting. Maybe another way to say this is like, if you look at all these, at the category of these categories enriched over quantile, then that's an order enriched category and not a two category. So we are in a simpler setting than if you work with categories in the usual sense. Okay, so here it's just like I said before, relations play an important role. So I define what a relation is here. I just want to use this as opportunity to say that if you work with non-commutative quantiles, another technical difficulty we get is that the opposite of a category is not a category anymore. Let me make this more precise. If I have a category or a space X and I take the opposite, then it's not a category over the same quantile. It's a category over the quantile where I reverse the multiplication. So the kind of standard categorical construction of taking the dual category, usually you stay in the same category of categories when you do that, right? You have a category, you dualize it, you're still in the same category of categories. That's not the case here anymore. But dualize, you go into a different category of categories, right? And you can imagine that there is all kinds of technical stuff available that doesn't work anymore. Actually, already when we define what a relation is, we can't simply say it's a functor from x up to times a into the quantile, because x up and a are not even in the same category. So it doesn't make any sense to say a or x up times a, but there is no Cartesian product of these two categories because they're not in the same category. So the way this is traditionally done is just to define this kind of from scratch, right? So we define what a profunctor or distributor or weakening relation or monotone relation is just by writing down the obvious definition of what it means to be a functor from x up times a into omega. By the way, if you read this logically and you read the multiplication as an and, then this is really just, you could read it as saying if x prime is smaller than x and x is related to y, okay, so now we have relations, we can compose them. So the first line you see an instance of this, I mean, this is kind of obvious, right? So, but anyway, so we have the quantile notation, that's the center dot, and then we have kind of the black bullet notation, which is on kind of one level of abstraction higher, right? So relations are predicates. So we are kind of moving up from kind of talking about objects to talking about properties of objects. And then we've seen that with the white triangles, right? So the center dot is, the multiplication is residuated, and the same happens here for the multiplication of relations. And then, yeah, so these four inequations are just another way of writing down the two adjunctions. And they are very familiar properties of relations. Okay, so I already, when I talked about the magnetic completion, I said that the magnetic completion is given by the fixed points between these operations, the up and the down operations. So these are actually adjoint to each other, and they form an adjunction between downsets and upsets. So I call this here fuzzy downset and upsets now because we're working Quantale and Enriched, right? So they're not kind of literally upsets, but it's fair to call them upsets or downsets because the math works out exactly the same way. For example, like what is the distance? When is the downset phi prime smaller than a downset phi, right? So this definition here defines the metric, if you want, on downsets. But to understand why the formula has to be the way it is, you don't have to think about the metric at all, right? So the formula just is, the formula is obvious just by thinking of what the formula means for upsets and downsets. So phi prime and phi are sets. When is a set phi prime smaller than a set phi? If phi prime is a subset of phi, right? And that's basically what the formula says, right? The nice thing here is that the formula works for metric spaces as well, and for fuzzy predicates on metric spaces. So I find this really beautiful, and I think that is something that has attracted researchers to that area ever since Levier wrote his famous paper in 1973. Yeah. Not yet, but you can make, you can treat the Hausdorff distance in that way, but you would have to define what the power set functor is on these guys, and then you can kind of extend the metric to that level. Yeah. So the Hausdorff metric corresponds to the side. Maybe you can think of, like, that's what you get when you talk about convex subsets, not downsets and upsets, but sets which are also note that implicit in this definition is that the order on the upsets is the other way around. It's not inclusion, it's reverse inclusion. Do you see that? So this is the smaller set. that is of course something that people who work with non-commutative quantiles like Peter does, they pay a lot of attention to make the notation kind of work without having to think all the time which way around things should go. Okay, so now the Magnier completion we talked about already in a little bit more detail. So we see the downsets and the upsets up there, the two functors, mapping downsets to upsets and upsets to downsets. And that's an adjunction. The proof that this is an adjunction works exactly the same in the enriched setting as in the two-valued setting. So with the notation as it's set up, it's the same proof. And then, yeah, the Magnier completion M of I is the set of fixed points either way, right? So it doesn't matter whether you take the fixed points of the downsets or the fixed points of the upsets. And yeah, so the vertical arrows are the Yoneda embeddings, right? So we have the contravariant or the ordinary Yoneda embedding on the left into the downsets, and sometimes called the co-Yoneda embedding into the upsets on the right-hand side. So this is all kind of very standard, both lattice theory and category theory. Yeah, this M is for Magnier, right? M for Magnier, and yeah. So now we looked at this picture. Here are some of the laws we can use. So the first law is actually interesting because it's saying that taking upsets is left adjoint to taking downsets if you read it, right? So if you remember my definition from the previous day, I still have it here. So the first equation says taking upsets is left adjoint to taking downsets. But then we know that in every quantile we have this equation for the white triangles. So that's a standard kind of fact about. I asked Peter whether this fact has a name, and I think we agreed to call it something like associativity. So it comes from the you prove that using the associativity of the multiplication. And then if you think about what does the associativity of the multiplication means for the residuals, then it's that equation. And you see that it's the same equation. If you lift it from quantiles to subset, it becomes the statement that taking upsets and downsets is adjoint to each other. And then the other laws are saying something like that if you actually go up with the Yoneda embedding, then that's already a fixed point. No, that's actually not true, right? If you go up and to the right, then you have a fixed point. Okay, so anyway, so the other laws are about the Yoneda embedding. So I've been talking for too long. I don't want to say anything that is wrong here. So it's just the purpose of the slide is to point out that we have this calculus, and it derives directly from the calculus from the algebraic laws for the quantile, and these laws are all very familiar in the two-valued case, and they work exactly the same way in the many-valued or quantile enriched case. I think we're going on with the time, so I can skip that. This is basically just some more of these equations. But maybe the interesting thing here is like what is written in gray at the bottom of the slide, which is that this incident relation, it specifies a distance between, say, objects and attributes, right? Now, you take your objects and your attributes, you embed them into the Magnier completion, right? So the magnetic completion is a metric space. So you need to have now distances between any two objects you pick, right? So it's kind of interesting to have formulas which compute these distances from just the incidence relation, right? Because the incidence relation gives you just distances between an object and the distance between an object and an attribute. Now you also need to get it the other way around, right? And two objects or from an attribute to an object, etc. Right? So that's what these formulas are doing. And then here's a version of the Yoneda lemma for the magnetic completion. So basically, it's easy to if you have an element X, right, which comes from downstairs, and you want to compute the distance to an element in the magnetic completion, that's easy. That's just the Yoneda lemma. And vice versa, the distance to a point that comes from upstairs is easy to compute. That's just the Yoneda lemma. So we have distance from and distance to, and because these metric spaces are not symmetric, these are not the same, right? The distance from X is not the same as the distance to X. And actually it's the distance from the axis, which is easy, and the distance to the ace, which is easy, right? So maybe one thing to take from that is that you choose the side you want to work on, depending on what you want to compute. Okay, so maybe I skip the weighted limits and co-limits, or maybe I can make it short. We started a bit late, right? But I don't want to overrun. No, but I should say a little bit about weighted limits and co-limits, because this is really what makes the whole story interesting, right? So a limit and a co-limit in the order setting, these are just meets and joins, right? And now when we work in the metric setting, we have more limits and co-limits. And so, for example, if you think of the Lavier metric spaces, there are limits and co-limits which come from the addition, right? So I didn't really say that earlier, but the multiplication in the Lavier Quantale is addition, right? And then composition is the triangle inequality. And also now we have these, we don't have just meets and joins. We have more operations than we had before, which correspond to these weighted limits and co-limits, and they come from this addition. So addition is taking a co-limit, and the minus is the adjoint of the addition. So we have now in our logic, when we talk about metric spaces, we have not only meets and joins, but we also have addition and subtraction. So, yeah. That's right. Yeah, that's right. Yeah. Mm-hmm. Yeah. Yeah. No, but the logic is doing something, the complete is doing something for the logic, and that goes back to Johnson and Tarski, who invented this kind of concept of a canonical extension. It's this kind of particular completion of a poset, or they did it for Boolean algebra, then it was done for distributive lattices, then it was done for lattices, now it's known to work for posets as well. And so think about kind of ordinary modal logic. We have just standard modal logic. We want to prove that it's complete for Kripke semantics. right? So we know that modal logic is complete for the stone space semantics just by duality, right? But then proving completeness for relational structures which are based on stone space is actually not what we want. First of all, it's boring, it's automatic from stone duality, but also then whenever we create a model, say we want to construct a counter model to prove that something is not provable in the calculus, we need to insist on creating these stone spaces where the relations need to be continuous and closed, and it's kind of, right? So we want set-based models. So how do we do that? And that's that uses this idea of a canonical extension. So we take the stone space, and then we go to the set-based semantics. Algebraically, this corresponds to going from Boolean algebras to complete atomic Boolean algebras. And so the completeness here is used, the algebraic completeness, the order theoretic completeness is used to prove the logical completeness of a calculus with respect to a set theoretic semantics. And this is just a very powerful tool ever since Johnson-Tarski wrote this paper, and there has been a lot of work in this direction. So it can also be made algorithmic, and you can use this to compute first-order correspondence to modal formulas, and there's a whole kind of big research literature on building on this idea. Yeah, but thanks for your question, because I think I wouldn't have said this. And actually, this is kind of a crucial motivation for this work, right? So this is what we want to do. We want to generalize these applications of canonical extensions to logics where we have more than two truth values. And people have done this kind of by hand, kind of moving, right? So just, but we're interested in kind of setting up the category theoretic machinery so that you can just turn the handle and kind of get results. It's a typical kind of categories, what we like to do in category theory. And we like to unify isolated results. Yeah. Okay, so that's all I want to say about weighted limits and co-limits for now. And then, so what is the definition of the canonical extension now? So I spent so much time on the McNeil completion. So the canonical extension is a particular example of a McNeil completion, but we build it in two steps. So we start with our, say, objects and attributes, and then we go to downsets and upsets, and then we define a relation now between downsets and upsets and take the McNeil completion of that relation, right? So we build it in two steps. Actually, I don't have to work with all upsets and all downsets, but that's a technical detail that becomes relevant if you look at particular logics you want to investigate. So for now, this is not really so important to us, but anyway, so we want to keep the actual upsets we're looking at as a parameter. It's called capital F here, for F for filter, right? So traditionally, it's the set of filters you're interested in here. Think of just lattices, right? So filters are certain upsets, ideals are certain downsets. And obviously, you want to consider filters and ideals because they are related to, the definition of filter and ideal is related to binary conjunction and binary disjunction. So by manipulating the definition of what a filter is and what an ideal is, you can kind of capture certain aspects of your logic, basically, right? So the notion of filter and the notion of ideal should be a parameter. And then what is the incidence relation? So it's just the filter and the ideal not having non-empty intersection, right? So you think of a filter, which is the downside, an upset, and then you have an ideal, which is downside, right? And then they may overlap or not, but it's certainly interesting. If they overlap, that's an interesting fact, right? And so that's what the incidence relation is capturing. So now we have a many-valued version of this incident relation. So we can't just say intersection, right? So we need to think about what is the corresponding notion of intersection. And so this obviously needs to rely on our quantile operations. So we take this multiplication of the quantile, and then we take the join in the quantile. And that's just, if you want a number, a distance, right? It doesn't need to be true or false. It's not the, right? In the classical case, it's the intersection, that's true or false, that's two-valued. Here we get kind of a number, if you want, or a distance. And now that's it, right? That's the definition. You know already what a magnetic completion is. So we just take the magnetic completion of that incidence relation. So I think that's my last slide. Yeah, that's my last slide. So this is just summarizing this construction in a picture. So you recognize that kind of the magnetic completion thing, but now we start at the bottom with this incidence relation between filters and ideals. And then I just a central property of this canonical extension, which makes it interesting for logic, is what is called compactness. And you can say that you can formulate this using finite subsets of your filter and ideal. But you can also just say, if the meat of the filter, so I think that's what I wrote down there. Yeah, if you take the meat, if the meat of the filter is smaller or equal to the join of the ideal, then the intersection must be non-empty. That's one of the equivalent classical formulations of compactness of the canonical extension. And now you can see that, yeah, I advertised our notation by saying that it tries to be as close as possible to both category theory and lattice theory. So this is the compromise. This is an example of the compromise we reached here. So kind of, at least if you would be working with it for a while, I mean, of course, if you see this for the first time, maybe you wouldn't agree with that. Yeah, so one has to compromise somewhere, right? So you cannot get these vast generalizations without having to compromise on notation. Okay, I think that's what I wanted to say. So thanks for listening. Yeah, that's basically trivial. That follows immediately from the definition in our notation. Yeah. So this is kind of more interesting. This is where you have to work a little. The other stuff is just like it just falls out of the definitions.
Yeah. Well, so my question, just to repeat it, but it was answered, is that the other half of characterizing canonical extension is that it should be meet join dense and join meet dense. And Alex's response was what I hoped it would be, which is that is the easy part of it. That falls out directly from the definition.
Yeah, so basically, if you look at the inclusions here, they have adjoints, so that's what it.
Yeah. Good.
Yeah.
My other question had to do with McNeil. Its characterization in lattice theory is that it's the injective hull of the
right, yeah.
O set.
Yeah, that's.
And you also have an analogous fact here.
Yeah, but that's not our result. Yeah, so there's a very nice paper, maybe from 2019 by, I think he's from Japan, Fuji, 2E at the end. He wrote a very nice paper where he shows that this classical characterization by, I think, Bruns and Banaszewski of the magnetic completion works also in the Quantale setting.
Okay, good, thanks.
Yeah. I was wondering on your black triangle calculus, is there also a black fusion that you can lift up to that?
Or the black fusion is the bullet. It's a composition of relations.
Okay. Good. And another minor comment, Levere uses the upside down non-negative real numbers, which of course is great for metric spaces and for that intuition, but the same algebra comes in the form of just the unit interval with multiplication.
Right.
And then it's very nicely, for logic, you have 1 and 0.
Yeah, it's the same, yeah.
It's the same.
These are isomorphic quantiles, so
right.
Yeah.
And it's depending on which way you want to look at this as a topological space or a enriched kind of logic, multi-valued logic. It's useful to be able to
at the
back and
beginning,
forth.
I prefer to think about the 0-1 kind of version with multiplication, but because then I don't have to say 0 is top. It's kind of counterintuitive, right? But after a while, you get used to 0 being top. And it's actually kind of, I get more intuition out of thinking as distances, but by thinking about distances than truth values. But yeah, so obviously you get 2 different sets of intuitions from truth values and distances, and that you can just go between the 2, the math is the same. That's of course makes this whole area kind of more interesting.
Thanks for the talk. So as a follow-up to Drew's question, so in the ordered case, you have also the uniqueness of these extensions, right? There are unique extensions such that everything's a meet of Jones and general meets, plus this compactness. So is this also true for the categorified version?
Yeah, thank you. Yeah.
And more substantial question. So you mentioned metric spaces as a particular instance of this. So I assume that canonical extensions and McNeil completions of metric spaces will be some known constructions from metric spaces. So can you describe what these are?
Yeah, so this is really interesting and it gets quite complicated. So there's a paper by Willerton from 2013 who looks at particular metric spaces and what the McNeil completion, he calls it the ISPA completion. It's also sometimes called, I think, the reflexive completion in category theory, what that means for really for the metric. And that's a very nice paper with also some nice pictures where you can kind of see which points are added and so on. Yeah, but I think, yeah, it can be, so this is, if you want computing the McNeil completion in the particular case of Levere quantiles, now if you start with a different quantile, then you have to start over again, right? So it's not as, the general theory is easy in a way, right? But figuring out what for a given quantile these constructions are actually doing for you, that's harder. So we are aiming at these completeness proofs of logic, right? So for that we just need the general machinery. We don't need to understand like which points are added by a McNeil completion of something, right? But I'm actually very interested I would be very interested in looking at some examples, and I'm sure there are interesting things to discover.
Ooh, Alex.
Yeah, thanks.